Okay, thin spherical shell now. Okay, we have to determine what is the strain that is produced in thin spherical shell now. Till now we consider the cylinders only. In cylinder, two types of stresses are that are induced now. One is circumference stress, second one is the longitudinal stress. In circumference stresses, the stress is equal to, we have taken PD divided by 2T values now. And longitudinal stress is equal to PD divided by 4T and so on. Just by using the relations, we determine the strain that is produced in circumferential as well as longitudinal strain is also calculated. But here we are considering spherical shell. Spherical shell is nothing but it is in the form of ball. It is just we are considered sphere we have taken now. But having thickness is equal to very, very less now. Now, we consider thin spherical shell subject to internal pressure as shown in figure. The pressure nothing but in all directions it is same now. This I am taking just half of the spherical shell. The pressure is acting just in upward direction, as in just P is representing the internal pressure which is acting inside the shell now. And D is representing the diameter of the shell. This is known as the here diameter D shell now. D now. As a result of the internal pressure, the shell is likely to turn away along the center of the sphere now. But when pressure inside the shell, when it exceeds to the permissible limit, automatically it fails in such a way that it becomes two equal halves now. That is a tear in the middle as shown in figure now. Therefore, the total force acting along the center of the sphere in order to shear into two equal parts is given by P into the area of the cross section. This entire area is required now. P multiplied by, which is equal to P into pi by 4 D square now. The stress in the shell is given by, stress is equal to, is given by total pressure divided by the area of the cross section now, which is equal to P into pi by 4 D square. It is the total force that is acting now in upward directions divided by the resisting area now, because we have to determine what is the stress that is induced now. That is pressure divided by the area which resisting area required now. Resisting area nothing but here only the wall thickness just along it is there now. That means it is equal to, we can take it as now pi d multiplied by the here thickness now. So we can take it as pi d t now. So from this relation we got it is equal to PD divided by 4T, where P is representing the pressure of the fluid that is acting within the shell now. D is representing the diameter of the shell. T is representing the thickness now. Since the shells are made up of materials, the edges are joined by using welding or just by using the riveting process. At that joining section, that is intersection of the two plates now, it is having just weaker than that original materials. Hence, we have to take N is nothing but representing the efficiency of the joint. Then the stress induced within the rivet or permissible stress that is allowed is given by PD divided by 4T multiplied by N, that is known as efficiency of the joint. Okay, based on these relations, we are having one problem now. A spherical gas vessels 1.2 mm, 1.2 meters diameter is subjected to a pressure of 1.8 megapascal. Determine the stress induced in the vessel plate if the thickness is 5 mm now. That is a spherical gas vessel of 1.2 mm 1.2 meters diameter. That the diameter of the vessel is equal to 1.2 meters, which is equal to 1.2 into 10 to the power of 3 mm. It is subjected to internal pressure of 1.8 megapascal. That is 1.8 Newton per mm square now. The thickness of the plate is equal to T is equal to 5 mm now. That is from this relation we got stresses in the vessel plate is equal to PD divided by 4T. where P is equal to 1.8, already we have taken Newton per mm square, into D is equal to 1.2 meters, which is equal to 1.2 10 to the power of 3 in mm, divided by 4 into T is equal to 5 now. From this relation, we got 108 Newton per mm square, or it is equal to 108 megapascal. The second problem is just based on this same spherical shell now. A spherical vessel of 2 mm diameter is subjected to an internal pressure of 2 megapascal. Find the minimum thickness of the plate required. If the maximum stress is not exceed 200 megapascal, take efficiency of the joint is 80% now. So the given data in the problem is the diameter of the vessel is given 2 meters now, but we are converting all the dimensions into millimeters only. So 2 meters is equal to 2 into 10 to the power of 3 mm now. Internal pressure is equal to P is equal to 2 megapascal, which is equal to 2 into 2 Newton per mm square now. Maximum stress is equal to is given, that is allowed now. It is given maximum stress is equal to 100 megapascal, which is equal to 100 Newton per mm square now. The efficiency of the joint is given 0.8 now. Here given. So let T be the, according to our problems, we have to determine find the minimum thickness of the plate is required now. The relation is the stress induced in the plate is given by 5D divided by 40. This is nothing but actual values. But efficiency is only 80%. We have to take n values in denominator. From this relation, we got the stress induced is equal to given maximum stress 100 megapascal, that is 100 Newton per mm square now. P equal to 2 megapascal, 2 Newton per mm square now, and D is equal to 2 meters is given, which is equal to 2 into 10 to the power of 3 mm, divided by 4 into T. We have to determine according to our problems, multiplied by efficiency is equal to 0.8 now. And doing this calculations, we got to T is equal to 1250 divided by 100, which is equal to 12.5 mm now. Okay, the change in diameter and volume of a thin cylindrical shell now. Because of increasing in diameter, when the shell is subjected to, spherical shell is subjected to an internal pressure, the diameter increases now. That means the volume also increases. Here we have to determine what is the volumetric strain produced within the shell now. The volumetric strain is defined as the ratio of change in volume to its original volume. In order to determine the volumetric strain, first of all, we have to consider the certain dimensions such as the diameter of the shell, intensity of pressure, and the thickness we have to assume first. So for this one, I am taking let D is representing the diameter of the shell now, and P is representing the intensity of the pressure, internal pressure, and T is equal to thickness of the shell now. Here T is nothing but representing the wall thickness. Here we have to take this is equal to T now. Diameter is equal to only internal diameter, not to external diameter. We have to take D values now. P already is nothing but acting just perpendicular to its cross section now. So from this relation now, the stress produced within the spherical shell, it is given by PD divided by 40 now. So the strain in one direction is equal to, we can take it as epsilon is equal to, because by using the relations we are having, x small s is equal to, we can take it as a stress divided by the strain now. That is strain is equal to sigma divided by E, we have to take it now. So from this relation we are having the strain in one direction is equal to sigma divided by E into 1 minus 1 by m now. So sigma is equal to the stress produced within this spherical shell, which is given by PD divided by 40 E now, already we determine 1 minus 1 by m now. Similarly, the change in diameter is equal to, because this is nothing but representing the epsilon, that is change in length to original length or change in diameter to original diameter. If I take D is equal to, that is change in diameter to original diameter, then the change in diameter delta D divided by D is equal to, I am taking now epsilon D now. that is change in diameter to original diameter. From this relations now, delta D is equal to epsilon D multiplied by here D now. So the change in diameter is equal to, we are taking now epsilon into D now. From this values we got it now, PD divided by 4TE into 1 minus 1 by M now, because this is nothing but the strain produced in one direction multiplied by D values now. So from this relation here now, D already it is there now, it now becomes PD square divided by 4TE 1 minus 1 by M now. The original volume of the sphere is equal to V is equal to 4 by 3 pi r square pi r cube now. By using the relations now, 4 by 3 we can take it now. 4 by 3 we are representing this r values in terms of the diameter. That is r cube is equal to, we can take it as d cube divided by 8 values now. So by substituting these values in this equation we got in terms of d it is equal to 1 by 6 into pi d cube now. The final volume of the pressure is equal to, because here the volume of the cylinder that is increases now, V plus delta V is equal to, that is the final volume is equal to 1 by 6 to pi, because we assumed that the diameter of the shell is increased when it is subjected to a certain internal pressure. So it is equal to D plus delta D whole cube now. So volumetric strain is equal to, it is defined as the change in volume to its original volume. It can be represented as now, change in volume is equal to now 1 by 6 pi into D plus delta D whole cube, it is the final volume, minus initial volume is equal to 1 by 6 pi D cube divided by again initial value, that is the final volume to its, the change in volume to its original volume. Here 1 by 6 pi is the common term in denominator and numerator now. The remaining values is equal to D plus delta cube minus of D cube divided by D cube now. So, and expanding this equation to D plus delta D cube, we got D cube delta D cube 3D square delta D plus 3D delta D square minus D cube divided by D cube now. Here delta D nothing but here now. Delta D generally in previous case we have taken in one problem 0.3, we got it now. So delta D cube is equal to 0.3 into 0.3 into 0.3. It is equal to 0.027 now. This value is very less now. This value is very less when comparing with this diameter. And generally this the multiplication, the delta D square terms, generally it is neglected by comparing with the original dimensions. So on doing that simplification problem, by deleting approximate values, that nothing but the values will be very less. The final value we got now, it is equal to delta D cube in nothing but it is now deleted now. Delta D square term is deleted now. Moreover, here D cube in nothing but both are in opposite sign there. The remaining values is equal to 3D squared delta D into divided by D cube terms now. Because already this is nothing but neglected term now. It is also neglected. These are nothing but cancelled. The only one term is there which is equal to 3D squared divided by delta D divided by D cube now. So this is nothing but it is equal to the change in volume to original volume now. So it is equal to 3 into delta D. Here D cube it is there now. Here in denominator D cube, numerator D square is there now. The final value is equal to 3 into delta D by D, which can be written as 3 into epsilon, that is 3 times of strain produced in one direction now. So the volumetric strain is equal to, we have to determine that value volumetric strain, which is equal to, which is defined as the change in volume to its original volume. According to relations what we are having, delta V divided by V is equal to, finally we got it is equal to 3 into epsilon now. By using this relationship we got to change in volume is equal to final volume, which is equal to 1 by 6 into pi d cube now into 3. Epsilon is equal to PD divided by 4TE into 1 minus 1 by M now. So on substituting these values in this case now, 1 by 6 to pi d cube into 3 into this values. From these relations now, Here d cube it is there now, d square it is there, d is there. It can be written as rho into pi into d to the power of 4 divided by ATA into 1 minus 1 by m. This is treated as the value of change in volume of the spherical shell when it is subjected to an internal pressure of P as shown in figure now. Okay, based on the change in volume of the spherical shell when it is subjected to an internal pressure, we are taking one problem here. A spherical shell of 2 meters diameter is made up of 10 mm thick plates. Calculate the change in diameter and volume of the shell when it is subjected to internal pressure of 1.6 megapascal. Take E is equal to 200 gigapascal and 1 by m is equal to 0.3 now. The diameter of the shell is given here 2 meters. We have to convert the values into millimeters so that all the values that are existing in the problem now becomes only in millimeters, which is equal to 2 into 10 to the power of 3 mm now. The thickness of the plate is given 10 mm now, and the internal pressure is called 1.6 megapascal. It can be written as 1.6 into Newton per mm square now. Modulus of elasticity 200 gigapascal, which is equal to 200 into 10 to the power of 3 Newton per mm square now. It is equal to 200 into 10 to the power of 3 Newton per square. Poisson ratio generally it is represented as 1 by m. According to the problem, this Poisson ratio is equal to 0.3 now. The change in diameter is equal to, we got now Pd square divided by 40 into 1 minus 1 by m now. This value here P is equal to 1.6, D is equal to 2 meters, 2 into 10 to the power of 3 divided by 4 into T is equal to thickness, and E is equal to 200 into 10 to the power of 3 is given into 1 minus 1 by m is equal to 0.3, and substitute the values we got to 0.56 now. The change in volume is equal to, we got to rho into P into pi d to the power of 4 divided by ATA 1 minus 1 by m now. By using the relations, here P is equal to 1.6 pi, D is equal to 2 into 10 to the power of 4 to the power of 4 divided by 8 into T is equal to 10, E is equal to 210 to the power of 3 into 1 minus 0.3 now. So from this relationship we got it is equal to 3.52 into 10 to the power of 6 mm now. This is the final answer, that is here now. From this conclusion we got it now. When any cylinder or the sphere, when it is subjected to an internal pressure of fluid, the dimensions changes now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.